Today we define the wedge product using alt, and then explain why it is the real generalization of the 3D cross product. In other words, the cross product is not the main character. It is the regional spin-off. Let omega be an alternating k-linear function and let eta be an alternating L-linear function. Their wedge product is defined as k plus L factorial over k factorial L factorial times alt of omega tensor eta. So the wedge product is obtained by first taking the tensor product, then forcing alternation. Extremely efficient, almost suspiciously efficient. Before using one forms, let us say what they are. A one form on a vector space V is just a linear functional from V to the field. It eats one vector and returns one scalar. Another name is covector. So alpha of AU plus BV equals A alpha of U plus B alpha of V. Nothing mystical yet. The mysticism arrives later, because apparently it has a schedule. For two one-forms alpha and beta, the formula becomes very concrete. Alpha wedge beta equals 2 times alt of alpha tensor beta, which simplifies to alpha of U times beta of V minus alpha of V times beta of U. So wedge is just the antisymmetrized tensor product. Clean, useful, and dramatically intolerant of swaps. In coordinates, wedge already looks geometric. Here dx and dy are one forms. Dx extracts the first coordinate, and dy extracts the second coordinate. Dx wedge dy is minus dy wedge dx. And dx wedge dx is 0. Also, dx wedge dy evaluated on two vectors gives u1 versus 2 minus u2 versus 1. The signed area of the parallelogram they span in the xy plane. So wedge is recording-oriented area, not just random algebraic grumbling. The same antisymmetrization idea also applies to vectors. For vectors u and v, their wedge is u tensor v minus v tensor u. The result is called a bivector. Geometrically, it represents the oriented parallelogram spanned by u and v. So wedge is really the algebraic way to encode oriented area. Now move to 3 dimensions. The space of bivectors has basis E1 wedge E2, E1 wedge E3, and E2 wedge E3. If you expand U wedge V in this basis, the coefficients are the familiar 2 by 2 minors. Already the cross-product formula is lurking here, trying to act like it invented the place. Here is the crucial 3-dimensional miracle. After choosing an inner product and an orientation, there is a linear isomorphism J from bivectors to ordinary vectors. It is determined by sending E2 wedge E3 to E1, E3 wedge E1 to E2, and E1 wedge E2 to E3. So in 3D, bivectors and vectors happen to have the same dimension, and we can identify them. Purely lucky. Do not expect the universe to keep doing this for you. Once that identification J is available, the cross product is simply J of U wedge V. Expanding this gives exactly the usual coordinate formula for U cross V. So the cross product is not a separate mysterious invention. It is just the wedge product in disguise. After 3-dimensional geometry lets us convert bivectors into vectors, the disguise is famous, but it is still a disguise. This is why wedge is the real generalization. The cross product mainly belongs to 3 dimensions. The wedge product exists in every dimension. It works for vectors, covectors, forms, and higher degree alternating objects. And it records oriented area, volume, and their higher dimensional analogues. So wedge is the general theory. The cross product is just the 3D celebrity guest. So the story is this. Wedge product comes from applying all to a tensor product. For one forms it gives the familiar anti-symmetric formula. For vectors it produces a bivector that records oriented area. And in R cubed, because bivectors can be identified with vectors, U wedge V turns into U cross V. That is why wedge is the true generalization. And cross product is merely the three-dimensional translation.